Okay, YouTube, in our last video, we introduced the notion of a sample space. And in this video, what we're going to do is we're really going to explore what we mean by a theoretical probability. And so let's go ahead and dive right into this. We say that the probability of an event really is just a measure of the likelihood or chance that the event will occur. So we say that, chance, this is a key word here. Basically, what we want to probably indicate here is that chance is indicating that things are happening randomly. So we have random chance. We want to, basically forecast, how likely something is to occur. And so we say that probabilities are numbers between 0 and 1. Interestingly enough, that means that every number between 0 and 1 is a proper fraction, or, maybe equal to 1. I guess it could be, 1 or 0. But basically, I could say that they're all decimals also, between 0 and 1. So we say you can include 0 and 1. And we can express this as a decimal, a fraction, or if you like, a percentage. And so you can see this here, this kind of spectrum of likelihoods here from 0 to 1. And we would say that something that has a 0 probability of occurring, it basically is just really an impossible event, whereas something that has a probability of 1 is definitely certain to happen. And these actually, they happen. Like for instance, how likely is it on a 6-sided die where all the numbers are 6? You're going to roll a 6, and it's like kind of like 6 out of 6, no pun intended, with the 6 is there, but basically what you get is 100% of the time. So you notice that I said 100%, 1. You'll see underneath all of these values here, we're going to look at all of them here in a second, but underneath their initial values up there, we have a decimal, and we also have a percentage. And so really quickly, I do want to make a note that when a number is written as a decimal, okay, you move the decimal twice to the right to obtain your percentage, and conversely, with a percentage, you move the decimal twice to the left in order to get your decimal value. But basically, 0 is impossible. That's 0.00. That's impossible, so it's 0% of the time, whereas 100% of the time would be 100% of the time. Or 1 or 1.00. And now in between, we would say, noticing that we're writing these here as fractions, in between would be 50% of the time. So we say 50-50, that's like flipping a coin, likelihood you get a heads. I guess it's equally likely to happen or not happen. So I'm not going to say it's likely to happen. I'm not going to say it's not likely to happen. I'm saying it's perfectly fair in that perfect instance there, 1 and 2 chance. But we'd say anything over a 1 and 2 is probably more likely to occur than not occur. And of course, anything underneath a 50% chance is less likely to occur than it is to occur. And the closer it is to 0, it's more unlikely. The closer it is to 1, of course, it's more likely. So we see that we have a 1 in 4 chance here. That's 0.25 or 25%. And of course, 3/4 would be about right here. 3 in 4 chance, 0.75, 75%. So we can list these in 3 different ways here, but we need to be proficient at listing them as fractions. Fractions, okay? We have decimals, and then a percentage. And all of these need to be kind of in our repertoire of writing here. So we'd say ways of writing a probability. Okay, there are 3 ways to do this. So let's go ahead and explore how we obtain a probability in the first place. It's a pretty easy concept, but we'd say that the outcomes for a specified event are called a favorable outcome. And so let's recall that in my last video when we were talking about sample space, let's say I've got a 6-sided die that's perfectly constructed here with 1, 2, 3, 4, 5, and 6. Everything's equally likely to happen here. The thing we basically want to indicate is that an event, indicates a specific set of outcomes in the sample space. So for instance, if I said the event that you roll an odd number here, we can see that there are 6 possible outcomes in the sample space, but of course the event that we roll an odd would only have 3 outcomes in it. And so we're going to refer to the outcomes for a specific event as favorable outcomes. We would say 1, 3, and 5 would be favorable if what we're considering is the event that we roll an odd thing. So we'd say that is just an example here, but we'd say when all outcomes are equally likely, we say the theoretical probability of the event can be found using the following formula. And one thing I want to point out here is this. I want to say that basically this is what makes a theoretical probability a theoretical probability in the first place. Theoretical, okay, is basically assume outcomes are random, okay, are random, chance, and we'd say all outcomes equally likely. Well, you know what, I don't want to indicate that they're all equally likely. I don't want to say that. That would be a classical probability, but basically we would say this is without actually using data from experiments that we conduct. So if we were to just say, you know, I've got a coin, I'm not going to flip it and see how many times it actually does come out heads or tails. I'm going to assume that both of those are equally likely to occur. Then the theoretical probability would just be this. We'd say the number of favorable outcomes, or the number of outcomes, and we're going to give this a name here, in the event space. The event space is the space containing all of the outcomes that are favorable. And we say the total number of outcomes, but we'd say the number basically of outcomes in the, that's really bad looking right there. Let me change the in, sorry. In the sample space, So basically it's just a ratio, it's just a fraction. We can get a decimal, we can get a percentage. They're really easy to find. And as a matter of fact, I want to do that now. I want to have you guys try this. So let's take a look at just an example that's already kind of been worked out, but talk about how we write probabilities and how we interpret them and express them when we're getting values. So we'd say that a student taking a quiz randomly guesses the answers to 4 true-false questions. So 4 questions in a row, true-false. Says what's the probability of the student guessing exactly 2 correct answers. So if we had been doing this for realsies here, first of all, what we're going to do is we're going to indicate the probability by writing out the probability symbolically here. So it says the theoretical probability of exactly 2 correct answers if guessing randomly, writ symbolically. The interesting thing here is that we write probabilities using this P parentheses notation. And so I'm going to write this here. I'm going to say 2 correct. And so what we're going to point out here basically is this. When you look at the probability of something occurring, we say that the probability of an event A is written P of A. In other words, probability that a given event occurs. And that probability is always going to be the number of favorable outcomes in that event space divided by the total number of possible things that could have happened. And so the first thing we want to get used to is the fact that we write our probabilities this way here symbolically. And I'm going to say that P2 correct, this is really the probability that the event of guessing 2 correct answers occurs. Guessing 2 correct occurs. And so that's what we're really trying to forecast here. And so here's the way we're going to do this. We're going to find the total number of possible ways that we could answer 4 true-false questions, and then we're also going to find the total number of ways that are favorable in which we get 2 correct answers. And so we could have done a tree diagram here. We could have said first question, we could have said correct or incorrect, and then from there we could say, I could get correct or incorrect, and you can see how this pattern is going to basically fall down here, and we're just going to keep getting this tree. What you'll see over here on the left is basically all of the outcomes that are possible for 4 true or false guessing questions here. Written in roster notation. So we say, basically the outcomes that could happen, we could get them all wrong or we get them all right. Or we could get the first one right and then the next 3 wrong, or the first one wrong, next one right, and the next 2 wrong. But basically, you can see that it's listed here by number of correct. But as you look at this, we can see that the total number of possible outcomes, let's count it up here. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 total possible outcomes. And of those outcomes, we can see that the favorable ones, where we get exactly 2 correct answers, I count 6 of them here. And so the theoretical probability of getting exactly 2 correct when you're guessing randomly, we would write it this way. We'd say probability, and I'm just going to write 2 this time, 2 correct. We plant that in there, but we get a 6 in 16 chance. And so because I don't have a lot of room here, let's assume I had more room, we say that 6 in 16 should always be, if it's a fraction, reduced if you can. I notice that these both share a common factor of 2. So this would become a 3, this would become an 8. I can't reduce this any further. So I'm going to say it's a 3 in 8 chance, but I'm also going to produce a decimal here. So we're going to say 3 divided by 8. We get a 0.375, 0.375. If there's a 0, of course, there's always going to be on our probabilities for the most part. you should list it there. And then we're going to say this is our decimal value. We say so it's less than 0.50 or 0.500 or 0.5. So it's probably less likely to occur than it is likely to occur. And then last but not least, we're going to say that as a percentage, this would be 37.5% as we just navigate twice to the right with our decimal here. So 37.5%, again, less than 50%. So less likely to occur, to not occur than occur. Okay? Okay. So what I want you to do now is I want to have you give this a shot, this theoretical probabilities here, these next two thought experiments, and see what you get. So read through this first one here. We say a coin is flipped 4 times. What's the probability that it lands on heads exactly 3 times? So go ahead and give this a shot. What do you get? What do you get? So sample space-wise, I suppose we would have this same thought experiment that we just considered here, flipping a coin 4 times. So we're going to say there are 16 possible outcomes, and the question we're asking, or at least the event space we're asking here, would be how big. We'd say, well, the theoretical probability we're trying to find in the first place is the probability that we get 3 heads. And you know what, interestingly, I know that I'm going back and looking at this thought experiment here, and this has to deal with correct or not correct, but you can see that I could switch all my tree diagram here to heads and tails and kind of have similar outcomes. So if you were to look at this as I, kind of represents like a heads. And let's go with C in this possible case. So I'm going to replace all C's with the tails, in this roster notation. We'd say then exactly 3, and I believe we were concerned with heads. We would say how many instances do we get 3 heads? Well, if every heads here in this table is represented by an I, then 3 incorrect here, we would say, that would be this kind of row right here where I see all these 3 I's happening. So we say 1, 2, 3, 4, where we'd have exactly 3 heads. And so we would just say then the event space or set of possible outcomes is 4. We'd say then the probability of 3 heads would occur 4 out of 16 times, which is a 1 in 4 chance when reduced. There's our fraction. We get 0.25 as we get this in a calculator, which would tell us this is a, whoops, get stuck with that decimal sometimes. We say 25% chance of happening. So really less likely to occur than it is likely to occur. And then looking at letter B here, what do you get? What do you get? So read through this here. We say a couple of plans on having 3 children in their future. What is the likelihood that all of the children will be boys? So see what you get here. Start by drawing out your tree diagram and writing out your probability symbolically. So here's what I get. We say probability of 3 boys here. We're going to say is some ratio, and we would have to list out the sample space. We'd say, well, with respect to the first child, we say it's either going to be a boy or a girl. And then from there we could say, well, we get a boy and a girl, or a boy and a girl. We could have a boy boy, boy girl, girl boy, or a girl girl. And then coming out of the third child here, we would say at those points you could have also a boy or a girl, or a boy or a girl, or a boy or a girl, or a boy or a girl. So our efforts here were basically to list out the sample space. I'm going to start with the easy ones here. We could say boy, 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 or girl, girl, girl. We could also say first child is a boy, and then the second child is a girl, but then we either have a boy or a boy, girl, girl. We could have that happen here. Now going down the right side of our tree here, we have a girl, girl, girl. We could say a girl, girl, girl. Or we could have a girl, girl, boy. So girl, girl, boy. Or we could have had a girl, a boy, and a boy. So a girl, a boy, and a boy, or a girl, boy, and a girl. Oh my goodness. So in other words, we have 8 possible outcomes. So in our sample space, there are 8 possible ways this could happen. We say, well, how many ways give us all 3 boys? And looks like there's only one favorable outcome that would give us that in that event. So we say a 1 in 8 chance. We say probability of 3 boys is simply a 1 in 8 chance. And so you should have gotten on your calculator 0.125 or a 12.5% chance of occurring. Cheers.